Let's start with our section 2.2 here. Of course, in the previous chapter, chapter 1, we looked at how to graph a circle, right? You need just the center and the radius to be able to graph your circle. For a straight line, we pretty much need 2 points, right? Once you have those 2 points, you can draw a line. So based on that, they're saying sketching a circle or a line can be pretty easy. But what happens when you don't recognize a shape? You don't know what those shapes are going to be. Now, some of these will, of course, look familiar, but maybe some of those you haven't seen a graph in a while, and you may not know, am I going to have a straight line? Am I going to have a curved line? Or other shapes? So they're saying to graph such equations, we calculate enough ordered pairs so that it gives us a general idea of what the shape is going to be, right? Is it going to be, like I said, a curved line, something else? So let's start with our first example here. It's your basic square function. We've got y equals x squared. You'll notice we're coming back to our discussion for domain and range here, and they want to know the graph that we get. Is it going to be a function or just a relation? So what I normally do whenever I'm trying to graph points like these, I have 5 standard points that I use. If they fail me, I'll change my point. So I actually normally start out with -2, -1, 0, 1, and 2. Those are my 5 go-to points. Like I said, if they work, great. If not, or if we need more points, then I'll expand our numbers from there. So the idea is if I'm selecting these as my x values, what am I going to get for my y? So think about it. You have y equals x squared. So if your x is -2 squared, what are you going to get for the y value? Yeah, you're going to get a +4 here. So in that same way, if you did -1 squared, what are you going to get? +1 for 0, 0 for 1, 1 for sure. Yeah, and 2 times 2 will give you 4. So we've got our ordered pairs here, right? Yeah. You've got -2, 4 from here, -1, +1. This guy, of course, will be 0, 0, +1, +1, +2, and +4. Okay. Let's see what that will look like when we put it on our graph. So we've got 0, 0, and I may have to wing this one. 0, 0, I've got 1, 1, -1, +1, and I've got +2, +4, -2, +4. I think my screen is a little off calibration here. So when we connect those dots, I guess, what do we get? Let's see if that will do a better job. Oh, not too bad. I just can't graph. Okay, so we were at -1, 1, 2, and 4. Okay, we might have to try it on our smart notebook here. First of all, will this be a function or not? Yes, because all you have to do is think about drawing a vertical line through the graph and you know it's going to be a function. So yes, it's a function. Now, what can you tell me in terms of domain and range? Again, just to refresh your memory, domain is all the acceptable x values and range would be what y values you get from those x values. So in terms of graph, if you think about this, this arm, as it's going up, is also going to get wider, right? Because this arm is going to start coming out this way. On the right-hand side, again, as this arm of my parabola goes up, it's also going to get wider, which means it's going to keep going towards the right. So the idea is this arm is going to head to the left, this one is going to the right. So what kind of x values are okay to use in this function, y equals x squared? Yeah, you can actually use any real number for these x values. So I can I pick these 5 values, I can actually put anything in there and it's going to work with this function. So your domain is going to be negative infinity to positive infinity because I can use anything. There's no restriction on my x. So what does that tell us about our y values? What kind of y values is our function going to spit out? Sorry? 0 to infinity. You will notice we have no graph on the negative side of our y-axis, right? This is my negative y-axis right here underneath. There's no part of my graph that even makes it there. My graph is starting at 0 because that was one of my points, 0, 0, and you can see these arms are only going to go up, which means from 0, they are going to positive infinity. Now the question is, should I include 0 or not in my range? Yeah, I will, because 0, 0 is part of my ordered pair here. So I know for sure in this example 0 is getting included. So you're actually going to put a bracket on 0. So do we see how our domain and range are negative to positive infinity for the domain and 0 to infinity, including 0 for our range? Okay. So now think about this example here, number 2. Because we looked at square roots last time when we started section 2.1. Can I use all the 5 values that I just used in the previous example? The negative 2, negative 1, 0, 1, and 2. What restrictions does a square root give us? Sorry? No, not necessarily. You can use numbers that are not perfect squares and it would be fine. But what restriction does a square root give us? You cannot have a negative inside a square root, right? You cannot, because what happens when you have negatives? We get into imaginary numbers. And remember what I said, as a disclaimer, we're kind of thinking, right now we're just working with real numbers unless they tell us that we're not. So since these can only be real numbers, I cannot have a negative on the inside. So I can actually start with 0 and go forward. I just cannot use anything less than. To make our life easier, we will definitely use perfect squares, so my y values come out nice and clean. So we can do 0. And what is square root of 0? 0. Yeah, 0. So this guy's going to be 0. What else can I use it with? 1, which will be, yeah. Can I use 2?
No.
3? I mean, technically I can, but they won't give us nice, happy numbers. What's our next one?
4.
Yeah, 4. Which gives us 2. And one more. 9. Square root of 9 is 3. So your ordered pairs here will be 0, 0, 1, 1, 4, and 2, 9, and 3. And again, I will try, but I am not very optimistic on what this guy will come out. Okay. 1, 1. All right, let's go here. Let me see if I can find my grid for this one. There we go. No. You want to show up? Okay. Don't let me. So we're going to wing it. Okay. So this was number 2. Our points were 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. We had 1, 1. 4, 2, and 9, 3. So when you draw your graph, this is what it should come out looking like. Did we have that general shape? Yeah? Okay, can you tell me if this guy is a function or not a function? It is, right? Because again, if I draw a vertical line through this graph, it will only cross the graph at one point. So this guy is a function. And what can you tell me about its domain and range? For both of them? Okay, so how are we getting 0 to infinity for both of them? When we were picking our points for x, we said you cannot have negative values for x inside the square root, right? So that actually was an indication of what kind of domain our function would have. So we know our function can start from 0 with the x values, and you can use anything as long as it's a positive number. So you're actually going from 0 to infinity on your domain. But then how does that affect your range? So again, you will notice there's nothing on the negative side of our graph, right? So again, we're starting, think in terms of the y-axis. We're starting at 0, and what will happen to this arm as it gets wider? It'll go up, because it's going to get fatter also as it gets wider. So it will keep going right, but it's also going to head on up, which means it's going to go towards positive infinity. So that's why in this case, both your domain and range are starting at 0. So you include 0, and you're going to positive infinity. So that's going to be for our y equals square root of x function. Any questions on that? So we've looked at the square function, right? Y equals x squared. We've looked at the square root function. Now we're changing it up a bit, and you've got x equals y squared. So what do you think we should do for this guy?
It would be the same as we had y equals x squared, but then instead of filling in the x's, we fill the y's.
Very good, perfect, yeah. So you're basically repeating what you did in example 1, where you had y equals x squared, but how we selected -2, -1, 0, 1, and 2 for x. Now use those as your y values and work backwards. So you will actually have -2, -1, 0, 1, and 2 for the y values. So you are basically saying if x equals y squared and y squared is -2, what's your x going to be, right? So what will those numbers come out to be? You're pretty much reversing your table, right? So you will have 4, 1, 0, 1, and 4. So what will that graph end up looking like? So let me go ahead and do my grid. For x and y. So we have 0, 0, right? What will happen? 1, -1, 1, +1, right? Okay. So we've got 4, and 2. We've got 4 and -2. 1, 1, 1, and negative. So this graph is actually going to end up looking Did everybody get that? Yeah? Is this a function? No. No, because it's going to fail the vertical line test. So it is not a function. What can you say about its domain and range?
from 0 to infinity,
For-
for the domain.
for the domain. Do we agree with here, NC? 0 to infinity? Are you including 0? Yeah? Okay, again, look at the graph. There is no graph on the negative x values, right? Which means we're not using anything on the negative side. And the main reason for that is no matter what value you use for y, positive or negative, our x always becomes positive, right? So that actually tells you that we have no negative values for the x. We start at 0 and we go to positive infinity. So 0 to infinity, and what can you say about the range, the y value? Yeah, because as this arm goes to the right, it's going to keep going down, which means it's going to keep going down towards negative infinity. As this arm goes to the right, it will also go up, which means he's heading towards positive infinity. So in this case, you will have a range that goes from negative infinity to positive infinity. Now compare these to the domain and range from example 1. What are we noticing? From example 1. What happened with the domain and range? It flipped, right? What was the domain for my y equals x squared function now became the range. And what was the range for the original y equals x squared function? Okay, I didn't need to do that. Became, well, I lost my place. There we go, that's better. And that, of course, happened because we changed the size where we have the square on this, right? So if the first one you had y equals x squared, this one you have x equals y squared. So it's a parabola that's opening on its side. And if you actually notice between our examples for 2 and 3, you will notice this upper arm of my x equals y squared is actually the same graph that you had here for y equals square root of x, because what happens is if I rewrite this little equation, let's bring our y squared to the left and move that x to the right. If I take a square root on both sides, I'm going to get one positive, one negative root. These guys cancel out, giving you just the y. And you're going to end up with positive and negative square root of x. You actually get 2 graphs out of this one graph. So what happens here is this upper arm is actually the positive root, and this lower arm is negative. You remember how we had done this with, no, we may not have talked about semicircles. We haven't talked about them. I think we're getting ready to. But you'll notice the same kind of thing with semicircles is that positive root and the negative root. So this actually is what we did in example 2 with y equals square root of x. So this is just the entire parabola opening on the right. If I put a little negative sign here in front of the y squared, this parabola would be opening on the other side, so it would be left facing. That would be the difference. Okay, what do you think we can do with a cube root function? What numbers can I use for x? Hold on. Let me see if somebody else wants to answer.
0
0?
and 1.
Negative numbers.
Yeah, those will work. What else?
8.
Negative 8.
Yeah, they would both work. Because cube root is not as picky as a square root. So remember, with cube root, you put a negative in, you get a negative out. You put a positive in, you get a positive out. So you can actually use both positive and negative numbers. So 0. What else can I use? You said positive 8 and negative 8. Outside of that, what else can I use? You ready?
1 and negative 1.
Yeah, you can use 1 and negative. Again, you can use 0, 1, 2, 3, 4, 5, 6, 7, 8, and everything in between decimals, but we want happy numbers for our y value, so let's stick with perfect cube. So cube root of negative 8 will be, yeah, negative 2. Cube root of -1.
-1,
Yeah, -1 would be -1. The next one,
0,
0.
1, and 2.
Yeah, 0, 1, and 2. So what will that graph end up looking like?
Yes.
Okay, so we've got x values going from +8 to -8. 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4. So we had 0, 0. +1 gives you +1. -1 gives you -1. +8 gave you +2. -8 gave you -2. So you should actually get a function, or actually a graph, that looks like this. Kind of an elongated S-ish peak shape. And of course, will this be a function or not?
Yes.
It is a function. And what would be your comment on both the domain and range for this?
Negative infinity and positive infinity.
Yeah, this one actually you can kind of see. This arm is going to the left, so he's going to hit -infinity. This arm is going to the right, so it's going to hit +infinity. So as far as domain goes, it's going to be both. It's going to be all real numbers. Now, what about the range, the y values, vertically? Same thing, right? Because kind of the same concept we saw with the parabola. As this arm goes left, it's also going to keep going downward because it's going to get wider, which means he's heading towards -infinity here. As this arm goes to the right, it will also start heading up. Obviously, it's going to be a while before he heads up, but the idea is he will, right? It will go up, which means he's heading to positive infinity. So for both these functions, for both these values for this function, it's going to be the same domain and range, negative to positive infinity. Question on that? All right, here we go into semicircles. So we know our basic definition for circles is x squared plus y squared equals r squared when you're centered at 0, 0, right, at the origin. Then we have the -h and the -k part of the equation if you're not at the center. So for this part, we're actually assuming our circles are centered at 0, 0 at the origin, and they have a radius r. So as you can see in this little diagram over here, the upper part of my circle, the top semicircle, is going to come from that positive square root of r squared minus x squared, and the bottom semicircle is going to come from the negative square root of r squared minus x squared. So how do we come up with these equations? Let's take a look at that really quick. So this is our general form of the equation centered at 0, 0. So we're trying to get the y by itself, basically is what is happening in those equations. So start by moving that x squared to the other side. Now you've got y squared equals r squared minus x squared. And just like we've done in the previous examples, to get rid of a square, we use square root, which gives us one positive and one negative root. So your left-hand side will clean up. You get just y by itself. And here, you're noticing I'm getting two different ones. I'm getting a positive r squared minus x squared, and I'm getting a negative r squared minus x squared. So the one that's the positive becomes your top semicircle, and the one that's negative will become the bottom. It's literally just rewriting that equation and trying to get the y by itself. And if you will actually notice in your handout, I did have those steps, but I just wanted to show you how we came up with these. So remember, the positive one gives us the top semicircle, the negative one will give us the bottom, and then the r squared, of course, the r is your radius. Now, when we look at the entire circle, and we had done these examples in 2.1, the circle itself fails the vertical line test. So we know a circle is not a function, but now if I just look at the top half, ignore that bottom one, just the top half, if I draw a vertical line through that, I know it's a function. Same thing with the bottom semicircle. If I'm ignoring the top part, the bottom semicircle, again, if I draw a vertical line through just the bottom part, it's going to be a function. So that's why we can use semicircles when we're talking about functions. So how are you going to graph this next example?
It's gonna be a negative semicircle or lower half.
Yeah, and that's coming from,
Just the positive, negative.
yeah, so it's actually this negative sign, and I don't know how much you can see it up here on the screen, but you should be able to see it on your paper. So because I have that negative sign in front of my radical, this negative sign is what's telling me it's going to be a bottom semicircle. And then what's the radius of our circle? 4, yeah. So this negative sign makes it the bottom semicircle. And your radius is just going to be square root of 16. Which will be 4. So when you graph your semicircle, you should be able to do that, but again, I'll do this here on our notebook. What number is this? 555. Okay, so we have a radius of 4, and we know it's a bottom semicircle. So your graph, you're basically doing the same thing you did with the circle, but instead of going in 4 different directions, we only need 3 of them. So that's going to be 1, 2, 3, 4, 1, 2, 3, 4, 2, 3, 4. And I'm a little uneven on my points here, but you're going 4 to the left, 4 to the right, and 4 to the bottom. That's all you need, since we need to be on the bottom half of our graph. Now this graph is very different from all the other graphs we have done. The first thing you should notice is we don't have arrows pointing saying it's going to keep going in all these directions, right? Because this is part of the circle, which means it's an enclosed graph. It's not like a parabola where we can draw these little arrows or our square roots, cube roots, that it keeps going. So it's going to be restricted just between what you're seeing, which is going to affect your domain and range. So look at the graph, think about it, and tell me what the domain and what the range of this function is going to be.
Domain is negative infinity to positive infinity?
No,
No?
because it's not growing. That's it. This is it. There's no arrows to show you that it's growing in both directions. Amy?
The domain is negative 4 to 4 with brackets,
Okay.
and then range is 0 to negative 4 with brackets.
Okay. Almost on the range. Did you have your hand up?
Yeah.
It's negative 4 to 0.
Yeah, just remember it's interval notation, so we always write the smaller number first, the larger number second. So just coming back to what Raylan had mentioned, you cannot go to negative and positive infinity here, because my graph stops right here at this point at negative 4. My graph stops right here at positive 4 on the other side, and I'm only between these points here, right? So you have a restricted domain and range in this case. On our domain, we're only going from negative 4 to 4, but we do have points at those ends, right? So you can include your endpoints. And then for our, so that's our -4 here, +4 here. On the y-axis, this guy was -4, and of course, this is 0. So you can see on the y-axis, I am only restricted between those two numbers, 0 and -4. On the x-axis, I'm restricted between -4 and +4. So your range is just going from -4 to 0. It's not even going above 0 because it's only the bottom half of our semicircle. So translating that, it should take you but a minute. What do you think the graph will be, and what will your domain and range be for this one? So first of all, is this a bottom or a top? Top, because that's a positive radical, so it's going to be a top semicircle. And what's our radius for this guy? Yeah, your radius is 1. So if you don't want your graph to look too tiny, make your scale bigger on your x and y axes. So I would suggest either thinking of these in halves or quarters, depending on however big you want. If you think of quarters, that means your 1 is going to be at the 4th marker, depending. Because if you do just 1, 1, 1, your graph is going to be this little guy. Right? I mean, it's not wrong, but like I said, if that's how small you want to make him, then that's up to you. So this guy would be what, 6? So that was a radius of 1, and it was a top semicircle. So this graph will be and I think I'm going to do it in 2s. So that should be -2, +2, +2. But technically, like I said, it's in halves. So this is -1, +1, +1, and 0. So it's basically 0, half, and 1. 0, half, and 1. 0, half, and 1. Domain and range for number 6.
1, -1. Or oh wait,
Switch it.
oh, -1.
So smaller number first, right?
Oh yeah.
So you will go from -1 to 1. But what will our range be? Because now this guy is a top semicircle.
0.
Yeah, it's going to be 0 to 1 because we always write the smaller number first and then the larger number. So 0 to 1. I think that's it for semicircles. So any questions on these last 2 examples?
Hey,
Yeah, sure.
I guess I just didn't understand
Okay.
where you got
So-
your spots.
Okay, so what I did, hold on a second.